All right. This is where we left off with lecture 15, was with having discussed the atomic size and ionization energy. Okay? We noticed that those were explained by pretty much the same two tendencies behind the atoms, the distance of the valence electrons from the center of the nucleus and the effective nuclear charge. Now, we're going to discuss specifically the first, second, third ionization energy, and so on. Okay? Because not all electrons are the same. So when you look at, say, carbon has those 6 electrons, 1s2, 2s2, 2p2. Carbon is in the upper right of the periodic table. It's a nonmetal. So it's going to have a fairly high ionization energy, or I should say first ionization energy. And so you make carbon 1 plus, you're going to have 1s2, 2s2, 2p1. That's your first ionization energy. Now, every additional electron is going to be harder to remove than the electron before it. Okay? Ionization energy keeps on increasing as you remove electrons. Because there were 6, now there are 5. The remaining electrons are held even more tightly than they were before. Okay, so carbon 2 plus has 1s2, 2s2, no 2p electrons. That's your second ionization energy, and it's going to be greater than your first ionization energy. So every time you remove an electron, it gets harder. Now let's look at some other interesting cases. So let's hop over to fluorine, over at the end of the second row of the periodic table. 1s2, 2s2, 2p5. Okay. You remove 1, you get fluorine 1 plus, 1s2, 2s2, 2p4. You get F2 plus by removing the second. Second ionization energy is going to be higher, 2s2, 2p3. And then F3 plus, you look at the third ionization energy, get you to 1s2, 2s2, 2p2. Okay. So the third is, of course, going to be greater than the second ionization energy, but it's even bigger than you would think. Okay. So first, second, third. Okay. There's a great big jump there. And the reason is because the change going from the second ionization energy to the third. Okay. So fluorine's valence electrons looked like this. Those are the 7 valence electrons fluorine initially had. Okay. You remove 1, you get to the first ionization energy here. You remove the second, and that's the second ionization energy. This is what you now see. For 1s2, 2s2, 2p3, you have a half-filled subshell. And remember, half full, these 3 guys are now all the same. 3 electrons all pointing in the same direction. Resonance. A half-full subshell and a full subshell are special cases when it comes to ionization energy and electron affinity. Okay. So when you're trying to move away from a half-filled or a full subshell, then you're going to have to put in a lot more energy to do that. When you're making the jump to a half-filled subshell, then you're going to get a smaller amount of energy. Okay? And I can actually show you the numbers for that, perhaps. Some Egyptians believe. There we go. Okay, that's why I couldn't find it. All right, so here we have hydrogen, a massive jump when you get to helium. The massive jump is because helium has no valence electrons. It's all core. And removing a core, you're not just talking about removing a full subshell. You're talking about removing an electron from a full shell. Okay, very unhappy. Okay, so massive jump when you're trying to remove core electrons. Here's lithium. No, it's an s electron. There's no resonance. It's all by itself. Then you come up here to beryllium. Okay, it has 2 electrons. There's a higher effective nuclear charge, but no resonance or anything like that, so it's just a small jump up. Then you come down here to boron. Boron has 2 s electrons and a single p electron. That p electron is at a higher energy, not too much higher, but a little bit higher, and it is not incredibly happy. No resonance or anything like that. So there's actually a slight decrease there. Then you go up to carbon, and nitrogen, and each of those is an increasing effective nuclear charge. But then there's oxygen, all by itself, or a slight decrease. That's because oxygen, if you draw out its electron configuration, oxygen is (2s2, 2p4). Removing 1 electron, we'll take it to 2s2, 2p3. 2p3 means you have a half-filled subshell, and it's actually happier that way. Okay. It still takes energy to remove it. It's not like it's just giving the electron away for free, but it takes slightly less energy than for nitrogen. Okay, that's because nitrogen, is a half-filled subshell, so it's happier than oxygen is with a more than half-filled. And then there's fluorine, and then we come back to neon, and it has an entirely filled shell, nothing but core, very difficult to remove. But not as difficult as helium, because it's bigger. Its outermost electrons are further away. I should stress that what we're looking at here is the first ionization energy. Okay, these are all how much energy it takes to remove the outermost electron from the element in question. And then you see similar trends when you get down to the third row. Okay, sodium is way down here, slight increase for magnesium, then a decrease for aluminum, increase for silicon, an increase for phosphorus, a slight decrease for sulfur, increase for chlorine, and then way up high for argon, which again is lower than neon. So, the next row, we're going to go ahead and leave those off because that includes the transition metals, and things are getting kind of wonky there. But you can kind of see some of the trends, the same trends, I should say, or similar trends for the S block and the P block. Okay, slight increase, and it looks like a slight decrease. It's hard for me to tell when you go comparing the S electrons to the P electrons. Then increase, not actually a decrease anymore, just sort of steps to the right, maybe a little bit up, and then increase. Okay. So once you know that sort of exception to the trend, referring to half-full and full subshells, then you can predict when you're going to see massive increases. That will let you compare the first ionization energies of different elements, or different ionization energies within the same element. Okay. So, looking at, say, calcium. First off, what's its abbreviated electron configuration? Look at the periodic table. Here's calcium in the 4th row. And the previous noble gas is argon. So it's argon 4s2. So when should you see a massive leap in the ionization energies? It's going to increase every time, first to second, second to third. When are you going to see a massive increase? Okay, the first ionization energy takes you to 4s1. The second ionization energy takes you just down to argon. Okay. So that's the first IE There's the second ionization energy. So the third would actually be removing a core electron. So the third is when you're going to see a great big leap in ionization energies. You can also compare, say, nitrogen versus oxygen. Which one is going to have the higher first ionization energy? Okay, the general trend says, well, oxygen is to the right of nitrogen, so you would expect it to have a higher first ionization energy. But the exception to that is that nitrogen is 2p3, whereas oxygen is 2p4. Okay? Nitrogen is happy with a half-filled subshell. Oxygen, if you remove an electron, it will get it to a half-filled subshell. So oxygen is actually the lower, and nitrogen is the higher. So those are the trends with ionization energies. Now you need to be able to make predictions regarding ions. Okay? An ion is when what you get when you add or remove an electron to or from an element. Okay? So everyone wants to be noble. Everyone wants to look like the closest noble gas. Okay? So that means when you look at the periodic table, okay, sodium, the closest noble gas, is to its left, neon. Magnesium, the closest noble gas, is to its left, neon. But for sulfur, the closest noble gas is to its right, argon. For chlorine, argon. Okay. So in order for the elements to look like the closest noble gas, they will either lose, if they're a metal, they'll lose electrons in order to look like the noble gas to their left. And if they're on the right, if they're the nonmetals, they'll gain electrons in order to look like the noble gas on their right. They're trying to get the same electron configuration. So you look at sodium. Sodium's electron configuration is neon 3s1. Let me double check that. Yes, I'm awesome. Okay. It wants to look like neon, which means that it's going to lose one electron and end up as sodium 1 plus with only its core electrons. So sodium goes to sodium 1 plus. That's the ion that sodium forms. Whereas you look at chlorine. Chlorine is neon 3s2 3p5. It wants to look like the nearest noble gas, which would be argon. So it's going to gain an electron. And it's going to become Cl1 minus. Neon 3s2 3p6. So that is the trend for what kind of ions you form. Losers on the left. Metals lose electrons. Nonmetals gain electrons. Okay. Losers on the left. Losers on the left. Metals lose electrons. Okay. So when you look at how many they lose or gain, it can be fairly simple or it can be fairly difficult. And you can make these predictions even for transition and post-transition metals. Okay. So, look at the periodic table. For the nonmetals, it's straightforward. You just gain enough electrons to get you to the noble gas to the right. So the halogens, each of them is only one step away from the noble gases, so they gain one electron. They get a -1 charge. The chalcogens, the oxygen group, they gain 2 electrons. They get a -2 charge. Nitrogen and phosphorus, they're 3 steps away. They need to gain 3 electrons. They get a 3- charge. Carbon is 4 steps away. It would get a 4- charge. It never does, though, because that would be kind of ridiculous. That's a lot of electrons to gain. And carbon is pretty small. It really prefers to be sharing electrons rather than gaining or losing electrons. It can. It's just difficult. All right, and that is another 15 minutes. So we'll put an end to this lecture as well, and we will pick up our discussion of ions, talking about how you can predict what sort of ions the metals will gain in lecture 17.